Hello, everybody. Today, I'm going to take a little bit of a moment here to discuss complex numbers and some of the important things that you ought to know about them. If you're studying math or physics or engineering, they're pretty interesting, but they're also a little bit complicated at times. So, I wanted to gather a little bit of information and talk about some of the things that I think are important about it. Okay, let's start with just the basic form of a complex number. Usually, a very common notation is used as z. So a complex number can be written in the form a plus jb, where j is the imaginary number. You also see I. I'm going to use j in this presentation. So here I say that a is the real component of z and b is the imaginary component. But it's worth noting that both a and b are real numbers. Like a and b themselves are not complex. You can kind of think about this as part of the number. So a and b are like scalars that describe each component. Um, yeah, so just keep in mind that a and b are not complex themselves. They are real numbers that live in the set of real numbers. And the term real and imaginary are components that describe the actual total complex number z. And to extract these real components a and b, it's common notation to use this boldface or script RE and IM, which stand for real and imaginary, respectively. And when you write it in this way, you can just extract the real part of Z and then the imaginary part of Z. Cool. Now, from here, let's move on to thinking about a graphical representation of complex numbers. And ultimately, this video will focus on talking about the different graphical representations and why they are useful and helpful with calculations. So above we discussed the quotation mark components of Z. And to me at least, this language is reminiscent of describing vectors, right? And this choice of language is not coincidental because it's very natural to think about complex numbers as vectors in the complex plane. So the complex plane is very similar to the Cartesian plane, the only difference being that instead of having it being spanned by x and y, it's spanned by the real numbers and the imaginary numbers. So if we have some complex number z that's in the form of a plus jb, in this case there's an I here, um, but we can literally think about that as a vector where we have a in the real component, right, in this direction, and then b in the imaginary component, right? And then we can draw a line going from the origin to that vector, right? Like that's a very natural extension. The complex plane not might not be a very familiar concept, but you'll get used to it as you use more of these numbers, right? And I'm making a little note here that RE and IM can be kind of thought of as some sort of projection operation. It's not exactly like an operation, but you can kind of think about it as being a way that we can decompose a vector into its components in each of its axes. So in that way, you can kind of make that connection where they're kind of some sort of projection operations. Okay, so this graphical representation naturally leads to another interesting idea that turns out to basically be the most useful representation, at least for applications in engineering and in physics, or anywhere where there's some sort of dynamic systems. And we'll talk more about that in future videos. But for now, we want to eventually get to this form where we can write a complex number in this form where we have r e to the j theta. So that's kind of weird, right? Because up here, I told you that this was like a vector. So it's kind of like something that's in like rectangular coordinates. And this, I'm seeing like an r, like a radial component, and I'm seeing like an angle. Where does the angle come from, right? And it's just kind of unnatural, right? But we'll build up to it. So the first thing that we can do is kind of thinking about taking just this like pseudo Cartesian coordinate system and converting it to polar coordinates, right? So what I mean by that is let's take exactly what we just drew, and one small note is that now we're representing z with x and y just because it's pretty natural because we think about like the x and y axis. So we're going to try to describe z, the complex number z, in terms of x and y. Sorry, we're going to describe it in terms of r and phi instead of x and y, right? And you can see from this diagram that this r and phi is nothing more than like what we've seen in polar coordinates when we're just working with a regular Cartesian system, right? So we can make this conversion where instead of having an x and a y component, we can have an r component that describes the radial direction from the origin, and then a polar angle, in this case phi, that describes the angle of that vector from the x-axis, or in this case, the real axis, right? So the idea here is we want to change the system of variables from something in terms of x and y to something in terms of r and phi. And it's not too difficult to see that these two relationships are true. So the x coordinate is equal to r cos phi, and the y coordinate is equal to r sine phi. Cool. So we found relationships between x, y, and r and phi. So now we can rewrite our complex number with these new ideas in mind, right? So if previously we had, let's see, I don't know if I wrote it down anywhere, but think about this form, but instead of a and b, we had x and y. We had z is equal to x plus jy. And with the new equations, they both have an r, so we can add them together, factor it out. So we're essentially going to just get this cos phi term plus this j sine phi term, which is identical to what we have here. We're now just describing it in terms of r and phi instead of x and y. But I don't know, to me, like maybe we made progress, but this is kind of awkward. They're the same and arguably more unnatural coordinates to work with. And the whole idea of polar coordinates is to be able to sweep out like an angle and then go out a distance of r in that direction. It's a way of describing a point differently than in rectangular, but in this we're kind of using polar, but it's also in a rectangular form. So what I mean by this like sweeping out and shooting r, we have this little example here where what I mean by that is if I want to describe this blue point in Cartesian coordinates, I would say it's some distance in the x direction and some distance in the y direction. But the whole idea behind polar coordinates is instead of doing that x and y stuff, why don't I say, okay, I want to go out a certain distance r, right? And then I'm going to sweep out an angle until I get to that point, right? So I'm creating an entirely new way of getting to that point from the origin rather than going out some straight distance x and some straight distance y. I'm now thinking about it as going out in some radial direction and then sweeping out the angle phi. So I think that we kind of want to get to a point like that where we can do the same thing with complex, or we can do the same thing with our complex numbers where we can go out a certain distance and then sweep out that angle phi. But this isn't going to cut it. This is still in rectangular form. So we need something to bridge the gap from this funky rectangular form to a true polar form. And this is where we have this beautiful equation. We have Euler's relation. So we have this elegant relation that provides us with precisely what we need. And you might have seen this before. It says that e to the j phi is equal to cos, and those are supposed to be phis, the angles are supposed to match, but another way of writing is e to the j theta is equal to cos theta plus j sine theta. Cool. So what does this mean? This is telling us that we can write our complex numbers in a true polar form where they actually have a magnitude in a phase, rather than this like weird rectangular form where it's in terms of polar coordinates, but it's not really that like shooting and sweeping behavior that we want. So with this new relationship, we can write our complex number z in this form that we talked about earlier. We alluded to it here, but now we've kind of built the foundation, and hopefully this should make a little bit of sense. Because in the previous step, we got this equation here just with an r on front. So it's not a big leap to see that we can just replace the highlighted part here with the other side of Euler's equation and replace it here. So I want to take a moment to pause and see how illuminating this concept is. What this is saying is that complex exponentials rotate vectors in the complex plane. So I want to show you another Desmos animation that should hopefully bring a little bit of intuition behind this. So what I have here are two dots. This black dot is a movable dot that represents a complex number in the real and imaginary axis. So what I can do, what I can do is I can move this point up and down, and what do we see happens? I'm only changing the imaginary component here. So as I vary the imaginary component, what happens to that little point? It rotates. As I increase the imaginary component, you can see that it's rotating uh, counterclockwise, so in increasing phi direction. And as I decrease it and I go to negative numbers, it goes clockwise. So we can just see this animation shows us that by changing the imaginary component, we can sweep out an angle phi. And not so interesting, but if we change the real component, that just makes it a bigger circle that we trace out. So if I make the R value a little bit larger, we can see that now when we move it around, it traces out a larger circle. But the important part of this animation is that complex exponentiation leads to rotation in the complex plane, which is super, super, super cool. And this oscillation behavior, this rotation behavior, it makes sense, right? Because in Euler's formula, we're seeing these cosine and sine terms. So it might not be fully clear, but we should start to see this idea between complex exponentiation and oscillations or rotations in the complex plane. So I guess I'll make a quick note that an alternative presentation of this same thing is this idea of a phasor form, where you have like your magnitude r, and then you have this kind of angle bracket with your angle. And functionally, these two forms are completely identical, but a lot of times you'll see this in engineering classes to represent your signals. So that's just another form, but like functionally, they're exactly the same thing. So now that we kind of have an intuition for like how we can think about complex numbers in terms of rotating vectors, let's explicitly derive phi and r in terms of x and y, so we can actually start using these, right? So from the plot we showed earlier, if we wanted to describe r in terms of x and y, we can just see that this side length is x and this side length is y. So Pythagorean's theorem will give us this distance r. So we can write r as the square root of the sum of the squares of the side lengths, right? And to solve for phi, I guess this is a little bit trickier, but we can start off by just with the idea that we want to relate phi with x and y in some way. So x is, with respect to phi, x is the adjacent side and y is the opposite side. So we can use the trig identity that involves the opposite and adjacent side. So that would be the tangent function, right? So we can take the tangent of this angle phi, and we're going to get the opposite over adjacent side. So that'll give us that tangent of phi is equal to y over x. And then to isolate phi, we can just take the arctangent of both sides, and that tells us that phi is equal to the arctangent of y over x. Cool. So now we have this form, which is very beautiful and allows us to think about complex numbers in a very interesting way. And then we have conversion formulas that can tell us exactly what r and phi are. So now we can do an example problem to show kind of like why we might want to use phasors, why we might want to use this idea of like a polar form, right? So what I have here is an example problem where I have this relatively not so simple complex number. If I ask you to plot this on the complex plane, it's really not obvious like how you would even plot this. So I'm showing two approaches here, and I'll highlight the advantages and disadvantages of both, right? So first, you can do it with Cartesian coordinates. And ultimately, like at the end of the day, in order to plot with Cartesian coordinates, you need to get it back into this a plus jb form, right? So you have to get it into a form where you have all in the numerator, just some number plus j times some other number, right? So in order to do that, we need to we need to get rid of all of these j's in the denominator, which involves multiplying by the complex conjugates and doing a bunch of distributing with complex numbers, which is maybe not like super difficult, but it's definitely tedious, and it's very, very easy to make mistakes, right? So I skipped a bunch of the algebra, but I can promise you that this is not the preferred method to solve a problem like this. And we'll see in the example below why the complex or the polar form of the complex number makes a problem like this much easier to solve. But what we see is when we do all the simplification, we get this as our final answer, which we can plot down here. So what this is showing is we have negative zero point 0.1 in the x direction. So that's this little distance here on the real axis, and we go up 0.7 in the imaginary component. So that's going to be up here. So we can see that our point is right here, and it's actually on like a circle, right? And the length of that circle is going to have to actually do with the radial component in polar form, which we'll see in just a minute. And when you bring these two forms together, it's actually really cool. It gives you a lot of information. But in terms of calculation, I want to show you why I prefer the polar coordinate systems. So the reason that this is nicer is because these complex exponentials are really, really, really easy to simplify when you're multiplying and dividing them. Maybe it might be a little bit of extra work to get them into this form. Like for example, with just j, right? If I want to write that as a complex number, that means that I have no real part and just one in the imaginary part, which means that the magnitude is going to just be the square root of 0 squared plus 1 squared, which is just 1. And therefore I have like nothing in front. And then the phase is just going to be where it sits on the complex plane. So if you draw a quick sketch of just this number itself, 0 real part and 1 in the y part is just a vertical line going up, which is 90 degrees. So we can basically convert each one of these individual components that are being multiplied into their own polar form. And like for this one, so 2 plus j, in order to convert that, you would need to take you need to find the magnitude of this, which is going to be the square root of 2 squared plus 1 squared, which is where we get this root 5. And then we take the arctangent of the y component divided by the real component, which is where we get this phase, right? And the beautiful part, once we get all of our polar form for each one of the complex numbers, is we can simply just multiply the amplitudes, right? We basically have 1 times root 5 divided by root 2 divided by root 5. We see that these root 5s cancel, and we're just left with 1 over root 2, which can be rewritten as root 2 over 2. And then the angles, since they're exponentials, we just use like the exponential rule, right? So if we're multiplying these two numbers, the arguments in the exponents just add, and they all have j in them. So effectively what you're going to get is you're just going to get one final complex exponential with a j, and then the angle associated it is simply just the sum of the angles from the individual components. One thing to keep in mind though is that since these are in the denominator, they're going to have a negative side contribution. So you can think about pulling this guy up to the numerator, but when you do that, you're going to add a negative sign. So the way that I got this 98.13 is I summed up 90, 26.56, and then I subtracted 45, and then I subtracted negative 26.56, which is an addition, right? And when it's all said and done, you get this, which tells you that in this plot, what this is telling us is that we're tracing out a circle with magnitude root 2 over 2, which in terms of a decimal is about 0.71. So the radius of this is 0.71. So you can think about starting at the origin, and we're going to go out 0.71 radially. And then our angle, this 98.13, tells us how far to sweep out once we're at that radius. So we can go out 0.71, and then we're going to sweep out. And we know that right here is about 90, and then we'll go another 8 degrees, and there's our complex number. And we got the same result two different ways, but each one kind of tells its own story. And I think graphically we can already kind of presume that we're correct, but just to make sure, what we can do is we can take our final rectangular form and do the conversion that we did like here essentially, right? And what we see is we get the same magnitude and the same face. So voila, we got our complex number two different ways in Cartesian and polar form. And here's the plot. So I hope that this illuminated a little bit like the different ways that you can solve problems like this. And this is just barely scratching the surface. There's a lot more you can do with these different forms, and there's like very obvious applications for when you would want to use each one. I hope this helps.